Hi everyone, welcome back to another video. In today's video, I'm going to be talking about magnetic properties of solids. So let's start. So we all have in our lives at some point interacted with magnets and basically had our fun with magnets, right? So what is the exact definition? The exact definition of a magnet is anything that is producing a magnetic field or is attracted to a magnetic field is called a magnet, okay? Now we have a basic and a vague idea to what could or could not be a magnet. For example, we would not expect paper or wood, okay, to be attracted to a magnetic field, but we would expect, let's say, a coin of 1 rupees to be attracted, okay. So let's just extrapolate this knowledge of magnetism to the solid state chemistry. So we know how solids are made up of constituent atoms, molecules, and ions, right? Now, considering that this solid is made up of constituent atoms, okay, the constituent particle is an atom. Now, after moving to an atom, we know how atoms also are made up of its subatomic particles, which are electrons, protons, and neutrons, okay? Now, this subatomic particle, which is called an electron, is the main reason why I have to make this video today. Well, electron is the reason why solids can be magnetized, and we'll see how. This electron is actually a charged species, right? So this charged species called electron, which is having a negative charge, is showing two types of motions, because of which we can call this a teeny tiny magnet, okay? What are these motions? Let's discuss. The first one is the orbital motion of electron. We know how electrons are rotating around the nucleus, right? So whenever a charged particle is moving, it creates its own electric and magnetic field, right? So because it is moving around, not moving actually, but rotating around a nucleus, it is having its own magnetic field. The second reason is the spin motion of electron. This again is another type of motion which the electron is showing, which is on around its own axis, and this is also the reason why it has its own magnetic moment, okay? So the electron is having its own magnetic moment, or we can say that it behaves like a magnet, okay, because of two main things, which is the first one is orbital motion of an electron around the nucleus, and second one is the spin motion of an electron around its own axis. Now, we need to know what is a Bohr Magnetron, right? So we know how every charged particle should be having its own magnetic field, okay? Now, every electron in a system, because in a system we don't have 1, 2, 30 or 40, but millions and trillions of electrons, right? But every electron in a system is having some amount of magnetic moment associated with it, and that amount of magnetic moment is called the Bohr's magnetron. As you can see, the value is quite less. It is 9.27 into 10 to the power minus 24, okay, ampere per meter square, which is quite less, okay, but because this is just the magnetic moment of just one electron. Moving on, the solids are actually classified on the basis of this magnetic behavior into these 5 categories. First one is diamagnetic, second one is paramagnetic, then we have ferromagnetic, anti-ferromagnetic, and ferrimagnetic, okay? We'll discuss one by one what are these and how do we classify solids into these categories. Let's begin. So now, as I already said, that electrons are behaving like magnets, okay? Now, these magnetic moments of electrons are just arranged randomly inside a solid, okay? And the behavior of these magnetic moments, as in when a magnetic field is applied to it, will tell us which category they belong to, okay? So what could happen is that if we apply the magnetic field to this randomly arranged arrangement of the magnetic moments, the first thing that could happen is that they will arrange themselves in direction of magnetic field, okay? And if these magnetic moments do that, then we say that the particle is magnetized, okay? Or it could also happen that these magnetic moments, instead of arranging them in direction of the external magnetic field, they will arrange them opposite to the direction of magnetic field, okay? And in this case, we can say that they are repelled by the magnet, or they are opposite to what we call being magnetized, okay? So having all the basic idea, we'll start with what are these different definitions, and we'll start with the first one, which is called diamagnetic, okay? So in a diamagnetic, the first I would say the first criteria of being magnetized is having a electron, okay? Now every system is having an electron, that is for sure, okay? Because if there's no electron, of course there should be no atom, but that's not the case anywhere. Now in any system, if we talk about, okay, we know how in an orbital electrons are present like this, which means one is having an upper spin and the second one is having a lower spin, which is minus half. Okay. Now, these two, when they are present together, they cancel each other out because they are having opposite magnetic moments. That's complete. That's very obvious, right? And the net magnetic moment is going to be 0, right? So, in any system, if we are having only paired electrons, okay, every electron is present in its pair. Okay, let's say we have plenty of electrons, but all of them are present in pairs. Then all of them will be cancelling out on the magnetic moments, and the net magnetic moment is going to be 0. And that is the case with diamagnetic materials. Okay, they're having 0 magnetic moments because all the electrons are paired and there is no unpaired electron present. Okay, so the main examples which you guys have to remember, which is something which can be asked in exams, are salt and water. Okay, and also some other examples which you see around yourself, which of course wood. Okay, all these are diamagnetic substances. They can never be magnetized. Moving on to what is paramagnetic. Now, what is paramagnetic materials? Now, these materials do have electrons. Okay, they have unpaired electrons present, which can be one or more than one. Now, these substances are weakly attracted by magnetic fields. Why? Because, of course, the randomly arranged magnetic moments are maybe arranged in direction of magnetic field as and when the magnetic field is applied. But also the main thing is that they will lose their magnetism as soon as the external magnetic field is removed. Okay, which is not the case with something which we will see further. The paramagnetic substances will become magnetic as and when we apply an external magnetic field, but will lose the magnetism as and when we remove an external magnetic field. Okay, so the most important example here is oxygen, and this is something we should know. Okay, so we have this topic of valence bond theory, which we do in class 11th, I guess, and there we study how the electrons are filled inside inside the orbitals or inside the molecular orbitals of oxygen gas. Okay, and that is where we realize that oxygen actually is paramagnetic, and now we know the reason why it is paramagnetic. Okay, because it is having one unpaired electron in case of if we talk about only oxygen. Now we have ferromagnetic substances. Now, what is the case of ferromagnetic substances? These substances are attracted very strongly by magnetic fields, okay, and they are permanently magnetized. So, unlike what happened in case of paramagnetic, okay, they are permanently magnetized, and the magnetic moments are arranged completely in direction of the magnetic field which is applied. Okay, so it may be possible, it may be a possibility that the magnetic moments are arranged just like this. Okay, so they are arranged almost maybe in direction. Something is like this, something is like here, something again in direction, then something is here and there, and this something again in direction. So this will create a net magnetic moment, okay, which is not going to be very high but still going to be there. So that's why it is written weakly attracted, right? But in case of ferromagnetic, as you can see, all the magnetic moments are arranged directly in the direction of the external magnetic field, and that is why they are very, very strong magnets and they are permanently magnetized. Okay, they will remain magnets even after the external magnetic field is removed. That's what ferromagnetic are. Okay, and the main examples are metals, strong metals like iron, cobalt, nickel, gadolinium, and this is a very important example of chromium dioxide, which you guys have to remember. Okay, there's no doubts about that. Now we have anti-ferromagnetism. What is the anti-ferromagnetism? So as the name suggests, okay, there's something anti going to be about these ferromagnetic substances. Now here the magnetic moments are arranged in anti-parallel direction, which results in zero net magnetic moment. So as you can see, they are arranged, they should have been arranged directly in direction of the external magnetic field, but okay, there's one, as you can see, there's one above, there's one below, so they are cancelling out, then they are cancelling out, then they are cancelling out. Just like that, all of them will cancel out each other and we will have a net zero magnetic moment, and that's why they are not attracted. Okay, so they should be having ferromagnetic characteristics, but because of the anti-parallel arrangement of magnetic moments, the net magnetic moment that we get is zero. So that's the case here, and the most important example is this, which you definitely have to remember, manganese dioxide, a very important example which is definitely asked in exams. So do remember this. Okay, and the last one which we have is ferrimagnetic materials. Now what is ferrimagnetic materials? Okay, in case of ferromagnetic and anti-ferromagnetic, we have two extremes. Okay, in case of ferro, we have all of them directed in direction of magnetic field, and in case of anti-ferro, we have one is above, one is below, and net we have zero. Okay, in case of ferrimagnetic materials, okay, what happens here is that they are arranged into parallel and anti-parallel direction, but in an unequal way. okay, and because of that we will have a net magnetic moment. In case of antiferro, we have arranged in parallel and anti-parallel in equal manner, okay, that's why we do not have any net magnetic moment. But in this case they are arranged in unequal ways, and that's why we will definitely have a net magnetic moment. As you can see here, we have two in the upward direction, one in the lower direction, then again two in the upward direction, then one again in the lower direction, and then we have finally a magnetic field into the above direction, right? So these are the examples of ferrimagnetic substances which you need to know of, okay. And this we have a small summary as to what is paramagnetic, anti-ferromagnetic, ferrimagnetic and ferromagnetic substances, and this is something which is important and we can remember by. So you can just screenshot this slide and keep it with yourself for maybe revision purpose. And thank you so much for watching. If you have any doubts in this video, you can comment that down below. For more videos like this, follow this page and stay tuned for more.